He's got a lab coat on. Oh my God. That's fantastic. Oh, that's awesome. Okay, all right, thank you. That was very, very beautiful. We should have put, oh. No, sorry. Oh, okay, yeah, sure. Okay, what am I looking for? Just go back in time, that'll show me. Here we go. All right, so then, after going on about big and little endian, hopefully less confusingly than I did just then. Oh, by the way, does anyone still have questions about big and little endian? I hope I didn't make it more confusing by talking about it then. Is there anyone that doesn't get the difference or wants to ask me any question at all? Okay, yes? Do I crack my eggs on the big side? I crack them on the little end. I'm a little endian. I just snack them like that. Snack down the middle? Yeah, Swiss. That's right. Okay. Then I talked about practice, and we showed that film by the firm. And all I was trying to say with that is, it is very convenient if your fingers can do the stuff without you thinking, because it frees up your mind to do the important stuff. As people, we're good at some things and crap at other things. If you had to add up 100 numbers and not make a mistake, you couldn't do it, I bet. You'd make a mistake. I hope you couldn't do it. In fact, I remember once in my old days of being an actuary, and I was applying for an actuarial scholarship, and I wanted to apply for the government actuary scholarship. And I knew the government actuary, and he was a nice chap, and I thought I could work there, that'd be very nice. So I sat the exam, and they sent me out the public service entrance exam. And they said, before you can apply for this scholarship, you have to sit the public service entry exam. And the first question was, here's a page of 900 numbers, columns, and here they are on the other side repeated, and you've got to find any mistakes where one column didn't match the other. And I looked at it and thought, I can't work at any place that thinks that's an interesting thing to do. And I didn't even apply. I realised the public service was not a place for me. So hopefully you guys now accept that that sort of thing is something a computer should be doing, not a public servant. And the things that we do that are really cool are having good ideas and seeing insights and generalising and abstracting. So when we're programming, hopefully we're spending most of our time doing the stuff we're really smart at and hardly any of the time that we're crap at. And hopefully we get the computer to do all the stuff it's good at, and we don't get it to do the things that we're good at. So just writing the program, knowing the syntax, being able to get your style right, being able to indent right, being able to get type definitions right, just being able to do all that, it's no human being should waste their brain thinking about that. That should just be like a reflex to you, so your brain can all the time be thinking about the important stuff in the program. Does that make sense? So I was saying, this guy, when he's roller skating, or ice skating, or whatever he's doing, skateboarding, he didn't want to be thinking, oh, I need to, he didn't want to think about all those details, or he wouldn't be able to do his tricks. He wanted his body to know the balance, and he wanted to know the wheel. He wanted the wheel to be an extension of his body. So, like, you don't have to think about how to breathe. In fact, if you try and think about how to breathe, have you ever noticed you stuff it up?
Why did you say that?
Yeah, why did you say that? Oh, all around the room, people are dying. Yeah. But if you're lying there, and someone says, all right, we're going to start filming now, I want you to breathe normally, you're going, okay, how do I do that? And now it's all crazy stuff. Okay. You want it to be a part of your body so you don't even think about it. It's the same with practice. So you want to do that sort of elite stuff that guy could do on the skateboard. Really satisfying, and what a good life you'd have if you could do cool stuff. You want to make sure the crap stuff is just second nature to you. So you've got to practice, like the implication was he must have done to get to this point. And it's not as though the practice is the end in itself, but you just got to know that stuff to clear it out of the way so you can do the fun stuff. And it's slightly painful to know. I'd be lying if I said that it's easy to do that stuff, but I wouldn't be lying if I said it's well worth it. You've got to do a bit of pain at the beginning. Yeah, okay, but everything in life's like that. And once you can do it, once you pass through that pain, the rewards, woohoo, they're very good. And then we talked about why we have functions, because we introduced functions before we introduced loops, which was a very strange decision, some of you thought. And maybe you could think about it now and try and, I won't tell you why we did it, but we put a lot of thought into the order we're going to do things, and we decided we'd do functions before loops. And so we started using functions, then about a few days into it, I said, well, what's so cool about them? What's the point of these functions? And we saw they had three neat benefits. They gave us abstraction, they gave us code reuse, and they gave us namespace and scope. And then we started applying these things in the assembly language, so you could see what they really meant in an assembly language. Okay. Then we looked at some types. We moved away from just ints, and we started looking at other types. So, so we'd already done longs, chars, we'd done numeric types, then we started bringing in chars, and we looked at how to create our own types with typedef. And then going back to the craftsmanship side, we started talking about, do you always have to follow a convention? Like, for example, do you always have to say main declares an int, even if sometimes you can get away with main not declaring an int? Do you always have to return exit success, even though sometimes it's, it's quite clear and you can just return 0 and no one cares? And I was saying, well, you don't always have to do it, of course, but what you're trying to do, hopefully, is get into the habit of doing the right thing. Like, for example, I'm not very good at stacking potatoes, but I bet if I'd practiced, I could do that really well. And I'd be able to think about the important thing now, which is not stacking the potato. What's the important thing? Giving the lecture. But you see, they're just not knowing the technical stuff. This is why at lecturer school we have quite a long time stacking potatoes. That's right, so we don't waste time in the lectures. So we can just do, oh yeah, thank you very much. I cheated because one of the potatoes is unbalanced. I had to take a bit off. So we talked about getting into the habit of doing stuff. And the example that I gave a couple of years ago, when I first started talking about getting the habit, and it just occurred to me, just reminded me this morning, I was looking over some past year's notes, was this, that if you're driving along, oh, did I tell you this already? You're driving along the road, and there's a set of traffic lights ahead, and they're red. What do?
Speed.
We're sort of all conditioned and we just stop. And when I was a little kid and I used to deliver leaflets early in the morning and I'd get up long before anyone else in the world was awake and it was dark as anything, I'd carry my big haversack round and I'd trudge around the street stuffing leaflets into pamphlets, into letterboxes. And there was a big intersection near me and I used to love playing this game, which was I'd wait till I could see a car coming in the distance because you could see their headlights. Coming through the valley, you'd see the headlights start to sweep up and I'd push the walk button. And then I'd go and hide in the bushes. And the lights would very quickly at that time of day go through the cycle and they'd go orange, red. And the car would go and stop. And this would be like at 5 o'clock in the morning. And he'd wait there for a minute. And there's clearly no other car in sight. There's enough light you can see it, there's no headlights. It's absolutely safe to go through, you're in the middle of nowhere. And he'd wait there for a couple of minutes. And I think, oh, I have control over adults. And I just used to think how pathetic that guy was. I assume it was always the same guy, that would just stop whenever I pushed that button. But when I grew up, I realised, actually, no. Why did that guy stop there? And why have we got a society and a culture where we're so ingrained to stop at traffic lights? And why did he do it?
Because he might have run you over?
No, I was hiding in the bushes. He would have run me over if he'd seen me, I bet you. What's that?
He might not have seen someone.
He might not have seen someone, yeah. But in that case, I could mount an argument that it was very clear and you'd be able to see anyone. It was very well-lit intersection. Very, very well-lit intersection.
He's reasonably tired.
He's very tired, yeah. Look, you're on the right track. Shh. It's against the law. No, I don't want... Yes?
It's kind of like a sheep mentality. It's like people that jaywalk, if there's absolutely no cars in sight and still wait at the light.
Yeah, some people don't cross even when they can. They don't optimise even when they can. That's right. Because no one else is doing it. And if someone starts walking, everyone walks. Yes? We're all pretty silly. That's certainly true. Thank you. Sorry, I hadn't got that you were saying that whole thing. I'm glad you kept talking. Yes, we're pretty silly and breaking the rules when it's okay to break the rules is, of course, completely okay. And breaking the rules when it's not okay to break the rules is potentially catastrophic. How do you know when it's safe to break the rules and when it's not safe to break the rules? You make a judgment call. How good are your judgment calls? If I'm cycling along, if I'm driving along on my bike, zooming down the highway, and it's this long highway and there's all these intersections on the side, what could happen if there's no traffic lights is I'm looking left and right at every intersection as I approach, trying to see what people are doing and where they are and if some idiot's going to kill me, because people like killing cyclists. So I'm cycling along, looking. But if there's traffic lights, I don't have to be cautious. I just zoom ahead. And in my car when I'm driving, if there's traffic lights, I can whiz down the highway at 80 kilometres an hour, even though there's cars that want to be in front of me. And I can do that because the red light tells them to stop. So I know it's completely safe to drive straight ahead at 80 kilometres an hour, and I don't even have to think. And I put my mind onto other things while I'm driving. Now suppose you're in a red souped-up car, brum, 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 and you're waiting off the side, and you can see me coming in the distance, but I'm a long way away, and you know your engine to a T, and you know everything about it, and there's so much time, Granny could walk out there in front and get away before me coming, and I'm the only car coming. You're in the car, brum, 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 you pull out, and you're completely safe. You've broken the law, but you've increased efficiency, so it's a good thing. Now suppose I'm a little bit closer. I'm a little bit closer, but you know your engine quite well, and you know my speed quite well, and you're very good at assessing speed, and you can see you can get out in front of me, and there'll probably be about 2 seconds to spare. So you go, again, everything's cut nice and fine, efficiency's improved, law's broken, who cares? Now then you're thinking, no way, I'm the world's best rally car driver, and I can do double declutching, and I can do handbrake turns and things, and I know the acceleration of I know Richard's speed exactly, and I can sense he's about to slow down, and you pull out and you scream out with 1 second to spare, but because you know all that, okay. Now the problem is, when you're driving down the road, and you make it, because you're the world's best driver, and your car's going doof, 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 and it's big and red, okay. But the problem is, me driving down the road now, I don't know that you're the world's best driver there, and if I can't rely on you to stop when there's a red light, what do I have to do? I have to be careful. And if I'm coming to the light and I can see you going, rum, 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 what do I actually do? I actually slow down. And you can't drive fast. No one can travel around at optimum super speed if all the time you're having to allow for other people possibly doing crazy things. But if it's not possible for people to do crazy things, you don't have to think about it. And ironically, through that inefficiency, we get increased efficiency by being able to zoom around without thinking. Does that make sense? It's exactly the same with habits. If you get in the habit of doing something so you just always do it, then you don't have to be constantly making this value call about it's okay to break the rule now, it's not okay to break the rule now, because sometimes you might get that value call wrong. And even worse, if your code interacts with someone else's code and you don't trust their value calls, then you've got to go through checking all their code because maybe they've broken rules left, right and centre thinking it's okay. So better if we just all obey the rules without thinking, even though that's a terrible sounding thing to say, isn't it? Because we like breaking rules, but it empowers us because we can then trust other people if we know that they won't break the rules, and that lets us do more. Yes?
Pamphlet delivering schoolboys aren't the only people that hide behind bushes.
Pamphlet delivering schoolboys aren't the only people that hide behind bushes.
Also, just as easily be a police officer.
I could be a police officer.
Yes, who presses the button and
Oh, yeah. Police officers trying to entrap you. Yeah, that's right. You never know. What's that? Yeah, that's right. That's right. So, but I don't think we do it out of fear. I actually think there's an actual benefit in doing it. Even though, amusingly, it seems to introduce inefficiency, if it gives us constancy and reliability and predictability, that gives us more than compensating efficiencies, I believe. Then we looked at this idea of using an ampersand in front of a variable to find the address of the variable. And this is where we started to do the Zoolander thing about dereferencing pointers. You always got to be careful if you're talking about the thing or the pointer to the thing. Ampersand gives you the pointer to the thing. So you've got to just practice that. And we looked at this concept of passing by reference. That normally we pass by copy, but using ampersands we can pass an address in which is copied in, and that gives us a pass by reference. And we spend quite a long time talking about the difference between pass by copy and pass by reference. And the reason we're doing it now, at this time in the course, is because I know that in a week or so, it turns out to be 2 weeks because we slowed down a little bit, you're going to be seeing arrays. And arrays are always passed by passing their addresses around. So you needed to understand pass by reference before we got to arrays. And then I asked you to give me tips about how to get fit. And you gave me some fantastic tips. And the best ones were about motivation, ways of motivating myself, ways of getting in good habits. Because who's the weakest link in the chain when it comes to me getting fit? Me. Yeah. So we've got to have things that'll work even if I stuff up. And we've got to have, I've got a plan. If I just hope it's going to work, it's not going to work. So you gave me all sorts of really, Google's the weakest link. No. So you gave me all sorts of really good tips and they were fantastic. And hopefully at the same time you started to think yourself, gee, how can I practice my programming? How can I make sure I don't fall into bad habits? What are the bad habits that are going to lie in front of me? Yeah, where are the pitfalls for me?
So are you fit?
I've lost 1 kilogram a week over the last 3 weeks. So I'm not fit yet, but I'm getting there and I'm not going to stop. Just like you guys aren't perfect programmers yet. Shh. You guys aren't perfect programmers yet, but you're heading in the right direction. And that's all that counts. You will probably never get there in the sense that I find the longer I program, the more critical I get. So the more I'm aware of my shortcomings as a programmer. So although maybe I'm always improving as a programmer, hopefully, my goals are moving up even faster, even higher. So you will probably never get to be a perfect programmer, but you are all moving in the right direction, and that is what this course, first course, is about. We reflected on task 1. Mainly we reflected on task 1 because I wanted you to think about how you'd failed in it. Because in task 1, no matter how you approached it, invariably, you would have made some mistakes. And the whole reason we have a task 1 is to flush those mistakes out early so you can start to think, oh, this is what I do. These are the bad habits I have. This is the sort of mistake I make. I didn't start on time. I didn't test enough. My code's too messy to understand. I was too confident about this. Whatever. We wanted to flush all that out. So I hope you all thought about task 1 and what mistakes you made, because we're rapidly racing towards task 2. We introduced 2 standard files, limits.h, which tells you how big the various types are on your particular machine, like how big a long is and how big an int is and so on. And we introduced ctype.h, which gave you some operations on characters, like is it an alpha, is it a character, is it a digit, and so on. How do I convert it to uppercase, and so on and so on. And we looked at, again, this same thing about the address versus the contents. It's this old ampersand thing here, pass by reference thing, Zoolander problem. Then we got up to loops. Now, why do you think we're doing loops now? Well, we need loops before we can hit arrays. And you need arrays because I need you to see indirect addressing. Because up until now, you're addressing every variable by name, which doesn't let you do fancy things. So we need indirect addressing, and we can't have indirect addressing without arrays, and we can't have arrays without loops, so loops. But we spend as little on loops as we can. We only introduce while loops, which are the most general form of loop. There are other ways of doing loops that we'll show you in the last lecture, but they're equivalent to while loops. We then introduced the concept of a stack frame. And stack frames arose, we actually only started with frames, though you now we mean stack frames when I say frames. Frames arose when we were looking at how functions worked, especially in assembly language, and we were looking at how did they achieve this scope thing, that the variables in the function only belong to the function and didn't belong to the outside world, and how do we allocate the memory when they need a memory, and how do we free the memory up? And we decided we'd communicate with them through an interface type way. This is like our lead into interfaces through something called a frame. Then week 5, finally we jump into arrays. Oh, this is why C is so frustrating. We don't get to indirect addressing till week 5. In a decent programming language, no, sorry, C is a fantastic programming language. I don't need to make fun of it. In a decent teaching language, we could have got to indirect addressing almost instantly. A decent teaching language is, well, look, what's the problem with C? Why am I poo-pooing C? C is a fantastic language. I know, Max, you make fun of C, but you love PHP. PHP is written in C. Okay, C has strengths and weaknesses. We don't program in C all the time because of the weaknesses, but the strengths mean some critical things are always written in C, because C, for the things it's strong at, is fantastic. There's nothing better. C is good because it gives you full control and lets you access memory directly. It lets you do all sorts of low-level things. So your operating system is going to be written in C, your decent games are going to be written in C, any good language itself will be written in C. Any serious large-scale program where efficiency and speed is really important will probably be written in some sort of flavour of C. But one of the bad things about C, you've seen them yourself. Your major project, how many hours did you spend on your major project? How much of that time was spent productively using your brain doing intelligent things? How much of it was spent making mistakes and then trying to find the mistakes? The ratio is wrong. With C, it's too easy to make mistakes, and we are too fallible. If we were perfect, C would be a perfect language to learn. But we're flawed, and C makes no allowance for that flaw. C gives us no safety rails. Yeah, haha, you're stupid is in fact what the language was called, and they abbreviated it to C. I mean, that's an example of how it goes. So C as a teaching language isn't so good because we spend too long dealing with errors. Nonetheless, as you can probably guess, I think there is a good side to that. It's not all a catastrophe, because really errors are what's going to plague us our whole life as programmers. So let's be honest and confront them in our first course. You'll never have more errors than you've had in this course, so at least it's downhill from now. But on the other hand, it does mean some of the interesting ideas we don't get to because we spend a bit too long dealing with how to deal with problems. So it's a tricky one. It's a very tricky one. We looked at how you declare arrays, which means how you say when you ask the compiler to set memory aside for the array. And we looked at how you use them, how you access them, reading to them and writing to them. And we looked at how you initialize them. If you're going to use, there's fancy ways of initializing them. We're using the curly brackets at compile time. I mentioned that. And we talked, no, not in this week, in the next week, about the biggest danger with arrays. And what's the biggest danger with arrays? Thank you, C. What's our biggest danger? Overflow or underflow. C has no idea at all when you're in the array whether you're still in the array. So imagine C is your mum in the car and you're driving along. And the kids are in the back. And she says, Gwen, can you move one space over to the left? And Gwen shuffles on one to the left. She says, good. Oh, can you move one more space to the left, Gwen? No, it's still blocking me. That's good. Oh, Gwen, can you still move one more space to the left? Sound of door swinging in the wind. Okay. C's like that. It doesn't care if it's telling you to jump out of the car. It just keeps moving out of the array. So that's the danger with C. You can easily move outside the array. And now, that would be an annoying danger that leads to programs that behave erratically, except that evil people, or as we like to call them, naughty people, have discovered, not nice people, actually some of the naughty people are nice, which is very confusing. But people have discovered that you can exploit this behaviour to create vulnerabilities and attack software and operating systems and computer systems. So it's the biggest #1 security problem in the known universe is the users being able to manipulate the program and tricking it to access areas outside the array. So we don't want to ever see you guys doing that. We want you to check, we want you to be sure, we want some sort of certainty that when you access an array element, it's inside the array. It's not just one outside and you're saying that's okay, it's in the array. We don't go outside the array. And then we got to week 6. Oh, now I think we need to have another break now. What are we up to? Week 5. We did Total Eclipse of the Heart. Can we just see a little bit of that? Because that is just so funny. This is my favourite. I tried showing it to my wife. She didn't see why it was funny. Am I right in thinking this is just the funniest thing you've ever seen? What's that?
Who else do you know plays the bridge?
Yeah, that's exactly right. What do you think? Is it a funny thing that he can't sing, or that they're playing instruments, or that his pants are falling down? I just keep flipping between all three, thinking, no, that's the funniest thing. No, that's the funniest thing. But I was watching with my wife, and she didn't think it was funny at all until this bit. Come here. Come here. Ah. This guy. He's just standing there like this. That has to be the funniest thing I've ever seen in my life. That's so cool. It's very scary. It's probably more funny for me than it is for you because that was a really beautiful love song when I was growing up. And yeah. All right, let's go. So let's return to the notes. Did you guys also think that was funny? Yeah. A little bit funny? Yeah, a lot's funny. Yeah. It might just be me. But I can't believe how funny that is. Okay, so I think there'll be an exam question on that. You'll walk into the exam room and the ladies will be standing around all looking like animal and there'll just be ovens dotted around the room. And as you come in, they'll hand you a big thing. Your time starts. Yeah, that's right. Whoever's pants fall down first. Okay, shh. So now, at the end of week 5, Tim talked about arrays and then I came back from Hong Kong and we sort of were now passing the milestone. Once we'd seen indirect addressing, we were now able to tackle hard problems. By hard, I don't necessarily mean they're really hard to fit your brain around, just hard in the sense that they're bigger than the sorts of problems we've been facing so far. Big enough that we can start to run into the limitations of the naive approach in solving them. So we started to solve bigger problems. We again return to this problem of the address versus the contents. That's the biggest warning we can make to you, that people are fooling around with things. They often forget whether they've got a pointer or the thing. And you've just got to keep fixed in your mind at all time. Best if the variable name even indicates that to you. We returned to talking about pass by reference and pass by value, and we talked about it a lot. Because when we're doing a complex thing now, we're bound to be using an array, which means we're passing the array around. We need to understand we're not passing around a copy of the array, we're passing around the original array. So if I give you the array and you change it, I'm getting a changed array as well. You're changing what I've got as well. Yeah. And I think we talked about the example of your uni transcript. If that was passed by reference, and I gave you your uni transcript, here it is, and I'm passing it by reference, you can say, thank you very much, Richard. And then when my back is turned, you scribble out the D and you write HD. Not only does it change it on your transcript, but because it's passed by reference, it changes it in the university system itself. So it's an enormous amount of trust. If you give someone something by reference, you're trusting them to change your own data. So you need to know exactly when you're doing it and that you're doing it. But the convenience about it is it's very fast to do it that way. You don't have to copy all the data. You don't have to give them a copy. Then we looked at how we pass arrays, and then we looked at the importance of a good spec in advance. Does this sort of, this is like the project. We're getting you ready for the project. The importance of working out precisely what needs to be done before you set out to do it. And do you remember the example I used to demonstrate that? My magic trick. Remember? And we did the magic trick, but I didn't tell you the rules until after we'd done the trick. Some of you will have felt writing the project was a bit like that. You came up with the interface for your tute. Everyone was programming to the interface, and it wasn't until you were halfway through it that people started working out exactly what the interface meant, presumably to fit in with their code at that time. And so it's really important to work out everything in advance. Then we started talking about estimation, which might have seemed like a diversion. Remember we were starting to worry about how many ping pong balls you can fit inside a ping pong ball and things like that? How many ants fit inside a fridge? We were doing that for two reasons. One is we wanted you to think about how you do estimation normally is a classic way of doing top-down design. So it was a nice way of re-emphasising that. You break it up. You think, oh, okay, how many ants would fit inside, how many ants are as big as a pea? Right, so how many ants would fit inside a bottle top? Okay, how many bottle tops would go inside a glass? Okay, how many glasses go inside a small box? How many small boxes could I put inside my fridge? So this sort of top-down way of doing it, of breaking it into intermediate steps, lets you quickly come up with a good estimate. But the other reason is we're just about to start hitting big numbers. We're about to get to the stage, which you'll see when we do sorting and searching, of looking at programs, and some programs do 1 million steps, and some programs do 10 million steps, and some programs do 1 billion steps. And we don't want you doing what most people do, because they don't have to deal with 1 million, just think, oh, all those 3 programs did a lot of steps. We want you to know, no, one did 1 billion, one did 1 million. To us, they've got to be quite different numbers. Because when we look at data structures, we'll see some data structures give us efficiency of 1 millionfold, and some give us efficiency of 1 billionfold. And if we do the numbers, we see the millionfold means I get the answer in 1 second, and the billionfold means I get the answer in an hour. So it suddenly is actually really important to get those big numbers right, because computers can go so fast and do such a big number of things. So now we need to, and store a big number of things. Now we need to really understand big things. And then we started talking about problem solving again. And this time I gave you some more tips. This time it wasn't about how to do top-down design or something like that. It was just about how you yourself should approach a problem when you're faced with a problem. And the first and number one step, and you'll hear me say it all the time, is the first thing to do is work out what's the most important thing. Skipping that step will lead to catastrophe. So don't rush in. Work out what's the important thing first. It's at least as important to work out the right data structure as the algorithm. And then we did the Sudoku as an example. And remember, we solved Sudoku in a lecture because we followed top-down design. When you're faced with a problem, you have to think about it and don't rush in. Now, I hope you follow that advice for the project. When you saw the project, did you rush in? No. When you saw the project, did you rush in?
Time not to.
You got to make me happy, okay? You can lie, it won't affect you at all. Did you? So when you saw the project, for example, did you rush in?
Yes.
No, no, you didn't. And did it all work out really well? Yeah, and did you have a great time? Yeah, and you were just thinking, oh, I'm glad I didn't rush in, it was fantastic. You warmed the cockles of my heart. I'm going to give you a potato. No, I'm not going to throw a potato at you. Not since the last court action. There you go. Oh, I'll throw it a small distance. Well done. Okay. Well done. So, planning, don't rush in. When you see a big problem, rushing in is just asking for trouble, because you will brilliantly solve the wrong problem. Brute force versus backtrack. And we started reflecting on how the Sudoku solver did, rather than doing a brute force, which we worked out would take longer than the whole universe, it did a backtrack, which solved it in a split second. Even though, on the surface of things, they both look like they're doing a lot of work, one solves it in a split second and one takes till the universe stops. We then returned to talking about frames and stack frames, and we started explicitly looking at buffer overflows and exploits. Then, this is all, we're building up now ready for abstraction. We're looking at how to solve bigger problems. We looked at this methodology called XP, which is extreme programming. And if you remember, there's a lot in XP, and we only talked about some of it. If you remember, what we talked about were, 1, in XP you work out what the most important part of the problem is and you solve that first. And it doesn't matter if it's not the whole problem, you just get something working first. So in the project, for example, you would get a stupid player working first that at least could just pass all the time unless it had control, and then it would play a random card. Yeah. So you would do the simplest, dumbest thing first. You don't rush into doing something complex. Then, when you've got that working, you do the next most complex thing. And then you add some extra feature. And then you add something and you build up slowly. But at all times, you've got something that works and is quite good. And remember I used the cannon analogy, which I stole off from the XP people, which is you could plan the perfect solution in your head. And that's like designing this brilliant cannon and doing all the ballistics. And you just have time to fire one shell at the ship, which I said was a French ship. And then someone from France was cross that I was criticising France. So let me say, it wasn't a French ship, I remember now. It was...
Comp 1911 ship.
Comp 1911 ship. No.
Microsoft ship.
A Microsoft ship. It was a pile of ship. And there's this ship just sitting out there. We've got a week to destroy the ship. We could spend the whole week plotting exactly the trajectory of the cannon, building the world's biggest shell, and at the end fire one shot. And if it's perfect, boom, the ship's destroyed, everyone's happy, you're the hero of the world, yay, hornblower. But if you miss, bip-bong, nothing. Much better is the idea to constantly try little things and make it better and better. So shoot whatever you got at it, shoot lots of cheap, crappy things at it. If they're not working, make them a little bit better, but constantly firing at it. So by the end of the week, at least you've damaged it and you've done something, even if you don't kill the whole thing. So the idea is, if you put all... Did anyone do this for the project? And I'm hoping the answer is no. Did anyone... I know, I'm a bit nervous to ask this question. Can everyone just say no to this? Did anyone design a very complex player in their head and then spend a long time programming it and have errors, and then in the end you really didn't get to submit anything? No. That's good. Because it's a danger. Yeah. The Mr. Pass takes about 20 minutes to write. Mr. Pass, it just passes each time, except when he's got control. All he returns is pass, except when he's got control. When he's got control, he returns a card. He takes 20 minutes to write. So, hopefully we all started with something very simple and built up. But if we didn't, that's fine. If we didn't, I don't want you sitting there now thinking, oh, bugger, oh, I didn't do that. Instead, I want you thinking, oh, I must remember next time, because this isn't the important time. It wasn't a real ship. The French weren't really attacking. It's okay if you didn't blow it up. In fact, it's good. This is just first semester, first year uni. It's a practice time. If you followed a technique and an approach to solving a complex problem that didn't work, that's actually really good. Because now you can think, oh yeah, next time I must remember to start small and work up, rather than starting really ambitious. And don't worry, in no time at all you'll be doing the amazing ambitious things, but just get the simple things working first. Shh, shh, shh. We looked at how to use asserts in testing, we looked at how multi-file projects work, we looked at how multi-file compilation worked. And then, most important thing, probably the most important thing in the course, dealing with failure with grace. We all fail all the time. That's life. Things go wrong. You can't go to pieces when you fail. You've got to learn from when you fail, but you just got to move on and be relaxed. It doesn't reflect on you. You're a wonderful person. You're a smart person. You're going to be very successful. There's no way at all is there anything wrong with you if you fail. In fact, there's something wrong with you if you don't fail. You're probably a replicant or something like that. We must fail, and the thing about being a human is when we fail, we pick ourselves up, we go on, and we learn from it. Okay, now week 7, abstraction. Woohoo! Now we're getting to the exciting stuff. Abstraction, we looked at the miracle, we looked at interfaces which make the miracle possible, and that led us to talking about ADTs and concrete, or concrete as I like to call them, and abstract types, and how we use those to program in the large. ADTs are probably the big programming concept in the course. The big concept in the course is this notion of abstraction. So we looked at samples of ADTs. Where are we with ADTs? We returned to XP and extreme ironing. We said start small, and I gave the Canon example. Oh, I gave it this week, not last week. Shh, shh. I said do unit testing and do it first. Don't do it last. Don't do it at the end. Do it at the beginning.
Is this your tag flash?
This is my blink tag. It's pretty cool, isn't it? Yeah. Don't do it at the end. If it's the most important thing, if it's the most important thing, and I'm telling you to do it at the beginning, what am I telling you to do? Unit test at the beginning. Yes? I'm telling you to be big endian. Yeah, yeah? Do the most important thing first. That's big endian. At the beginning, the important thing, the biggest thing. Yeah. Rather than the little endian. Yeah. XP extreme programming, start small, unit testing. At this point, we'd nearly reached all the syntax in the course. All we had left to go was structs, bit operators, and malloc. I talked about dealing with stress, talked about the difference between strings and chars. And then I asked the question, which I didn't answer. Why did we have this extra work in task 2? As a lot of people pointed out, you could have written a task 2 solution without an ADT. That would have just been very short and simple, and that would have solved Sudoku without needing to have the Sudoku abstract type. And having the abstract type gave us a lot of extra work because we had to worry about interfaces.h files, separate file compilation, and so on and so on and so on. Which sure was good practice for the project and all sorts of things like that. And But why is it also a good design decision to break it up like that? To make it more generic. And how can we make it more generic?
You could scale the problem up.
Thank you very much. Brett's got it exactly right. You can. It's Brett, isn't it? You are Brett. Yes, yeah. Phew. You can, without any effort at all, which is this week's lab exercise, change Sudoku to be a 4x4 Sudoku rather than a 3x3, to be a samurai Sudoku from the Sydney Morning Herald thing, to be a 3-dimensional Sudoku, to be a Sudoku on a torus, to be a Sudoku on the projective plane, on an n-dimensional Sudoku. You could change any of those aspects of Sudoku by changing a few lines of your code and everything will still work. Because you separated the two parts of the problem, the physical representation of the Sudoku board and the constraints on it, and the technique you used to solve it, which is backtracking. Because they were isolated into separate parts, we just have to change the physical structure thing, which is just a few lines, particularly if you're just making it 4x4, and it goes, and the solver stays the same. And can I also say, just before I get to your question, the other question I wanted to put in the lab, and maybe I will, you tell me if it's worth putting it in. I just want to put a couple of extra questions in so you can get extra marks if you haven't got them. You don't have to do them, there's just if you want them. It also lets us, if we have done abstraction right, we can take out the abstract module. Say this potato is your Sudoku grid.c. You can remove this potato and replace it with this potato. And if it's completely abstract, I have no way of knowing which potato you're using. Now, which potato is better? The one on the left. Oh, your left. Try and see. Okay, so you've already written a Sudoku grid, I reckon, which is reasonably good. It's like this potato. It's more or less good, but it's not as fast as it could be. And that's all right, because we told you fastness wasn't a constraint in the problem. I'm thinking we could have a lab exercise, which is, I want your Sudoku solver to be fast. Maybe you can solve 1,000,000 Sudokus in a minute or something like that. Can you change Sudoku grid.c just very slightly to make it extremely fast? And with an ADT, because it's done in an ADT, everything will still work. You just have to change how you represent it. So what do you think of that as a lab exercise? No, 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 no? Don't want it? No, you're doing something else. Okay. No, 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 no. No, I just want it to be faster because you've got a different ADT. You don't have to put it in. It's a puzzle to think about in the holidays end. How can you make it like 1,000,000-fold faster just by changing your representation slightly? And then we looked at the snake. And the snake was an introduction to linked lists. In week 8, we just did examples of ADTs, and they were very simple. And we talked about task 2, and I put it in an ADT and showed you what it would look like in an ADT. And we talked about stacks and queues and how to design an interface. And that was very simple. We're nearly there. We've got 5 minutes to go. In week 9, oh, let's go here, we'll look at another one. What are we up to? Total Eclipse of the House, Extreme Mining, Starship Troopers, the Australian National Anthem. Please no. Please no. Eurovision. Oh, yes. Or the German National Anthem?
Yeah, yes. In Old Norse. In Old Norse.
In Old Norse. That's a cool one.
We gaan door naar de meest bizarre act in de geschiedenis van het festival. Houd je vast, Finland. Dat rekent af met het veroordeel dat mannen...
It's from very beautiful Finland. It's very tranquil. Peaceful. Lovely.
3 uur in de machine voor zijn podium op kunnen. U ziet zo wel waarom. Het zijn monsters uit een horrorfilm. Compleet met vleermuisvleugels. En ze moeten
Very beautiful.
in 40 jaar deelnemen eindelijk een top 5 positie brengen. In eigen land voelen geestelijke vast van vergiffenis vanwege deze bloedstollende act. Maar de Lordies vinden hoe enger, hoe leuker. En bovendien verklaart de leadzanger Lord die dat bandjes die een shirt enzovoorts optreden, dat dat niks is. Zij willen de fans waar van hun geld bieden. Nou, dat gaat u krijgen bij Hard Rock. Halleluja.
That was a very interesting Eurovision entry. That's the Vikings coming back. There you go. Okay, all right, so yes, you can all check that out. That's probably my favourite Eurovision ever, that song. Okay, Week 9, I saw a personal trainer and it reminded me of my relationship to you guys when you were doing the assignment, in that I had to motivate you like he had to motivate them, though he was being paid and I wasn't. I'm only being paid in potatoes. Yeah. No, I mean, I don't mean I've got the same sort of intimate relationship with you that a personal trainer does, but in a sense we have the same objectives, which is to motivate. We looked at file I/O as an example of an ADT. We introduced linked lists. We talked about what we meant by clear and correct. And we finally got around to explaining what argc and argvig were. We explained how we marked the project and why. And the why was because we wanted you to do this incremental submission. We wanted you to do XP. We wanted you to start small and work up. Week 10, we're nearly at the end of the course. In fact, look, here's the end of the course. Dynamic data structures, we did more on linked lists. And we talked about the advantage of sorting a structure. We talked about binary search on a structure. We talked about binary trees. And then we talked about the project, which was wrapping up at that time. And I encourage you to, I told you you're all doing very well, because you were, and to think a lot about how you were going and your problems. So you reflect on how it's gone. And I mentioned how inspired I was by you guys, because I was at that stage. It was very inspirational for me. At that stage, you weren't giving up. Everyone was having exams and toughness, and life looked pretty black. And I was reading through people's diaries, and no matter how tough it was, everyone kept working. And I just thought that was fantastic. And hopefully that's all finished now, and you've just got the final exams. We did some tips. We talked about snarks versus boojums. And in week 11, we talked about ethics. We talked about... We talked about how, if you think of life as a big spec, the most important thing is to work out what's the big question to solve. And the big question to solve isn't how you live day to day or how much money you earn or something like that. It's things like, you believe in a God? Who are you going to marry? What do you think about love? What are your ethics? These are the big questions that we don't really think about very often, but they're probably the most important ones. So in consistency with my approach to saying always think about the important things, I encourage you to think about these things just briefly in advance, not necessarily about whether there's a God or not, but about ethics. I wanted you to think about it in advance, because when it comes to the test and your ethics is tested, if you haven't thought about it, you'll just do something random, and that's sad. So think about it in advance so you do the right thing when you're tested. That was all. Okay, so now we're up to, we'll finish off on Wednesday. We don't have to do any of that stuff. Don't have to do that, don't have to do that, don't have to do that. Okay, we're done. I'll see you on Wednesday.
If they pay you in potatoes, where does all the money we pay them go?
That's such a good question. How do you pay them? I assumed you just gave them baby potatoes.
No.
And they grew them carefully and then handed them to me. You actually give them money. Well, I've been labouring under a
yes.
Yeah, no, that's a very good question. I'm going to have to ask that question searchingly to someone.
I should head of school.
Yeah.
Maybe he's got this giant pile of gold.
He's got an enormous potato farm, I know that. Yes.
I had a question about the